Section 4.6 Solution Stoichiometry and Chemical Analysis. In Chapter 3, we learned that given the chemical equation for a reaction and the amount of one reactant consumed in the reaction, you can calculate the quantities of the other reactants and products. In this section, we extend this concept to reactions involving solutions. Recall that the coefficients in a balanced equation give the relative number of moles of reactants and products. To use this information, we must convert the masses of substance involved into the reactions in the moles. When dealing with pure substances, as we were in Chapter 3, we use molar mass to convert between grams and moles of the substance. This conversion is not valid when working with solutions because both solute and solvent contribute to its mass. However, if we know the solute concentration, we can use molarity and volume to determine the number of moles. Figure 418 summarizes this approach of using stoichiometry for the reaction between pure substances and a solution. If you have grams of a certain substance, you'll go through the periodic table to find moles of certain substance, then use the balanced equation to find moles of the second substance, and then use the molarity to go from moles to the volume of the substance containing substance B. Once you have the moles of a substance, you can use the volume of a solution containing B to find the molarity of the solution containing B. Titrations. To determine the concentration of a particular solute in a solution, chemists often carry out a titration, which involves combining a solution where the solute concentration is not known with a reagent solution of known concentration called a standard solution. Just enough standard solution is added to completely react with the solute in the solution of unknown concentration. The point at which stoichiometrically equivalent quantities are brought together is known as the equivalence point. Titrations can be conducted using neutralization, precipitation, or oxidation reactions. Figure 419 illustrates a typical neutralization titration, one between hydrochloric acid solution of unknown concentration and a sodium hydroxide solution we know to have a concentration of 0.100 molar, our standard solution. To determine the hydrochloric acid concentration, we first add a specific volume of hydrochloric acid, 20 mils in this example, to the flask. I'll pause here. Figure 419, procedure for titrating an acid against a standard solution of sodium hydroxide. The acid-base indicator phenolphthalein is colorless in acidic solution, but takes on a pink color in a basic solution. 20 mils of acid solution is added to the flask. A few drops of the indicator is added, which remains colorless. The standard solution of known molarity is added to the burette. The solution becomes basic on passing the equivalence point, triggering the indicator color change. A few drops of the acid-base indicator are added. The acid-base indicator is a dye that changes color on passing the equivalence point. For example, the dye phenolphthalein is colorless in acidic solution, but pink in basic solution. The standard solution is then slowly added until the solution turns pink, telling us that the neutralization between hydrochloric acid and sodium hydroxide is complete. The standard solution is added from a burette so that we can accurately determine the added volume of sodium hydroxide solution. Knowing the volumes of both solutions and the concentration of the standard solution, we can calculate the concentration of the unknown solution as in diagram figure 420. The volume of the standard solution, this is in the burette, is added to the moles of a solute in a standard solution, or we find the molarity of the standard solution to find the moles in the standard solution. We use the coefficients in the balanced equation to find the moles of the unknown solution we don't know the molarity of. And then from the volume, we know the volume that is added, we find the concentration or molarity of the unknown solution.